Good day, everyone. Welcome to lecture number 31 of this lecture series on computer organization and architecture. In this particular lecture, we will discuss the different operations that are related to the caches. After completing those operations, we will discuss a mathematical model for a memory system and in which stage of the pipeline we are going to access the memory system. And at the end, we will discuss the cache misses. What are the different types of misses that are there in the cache and how we can reduce those misses. Okay. So as I said, the first part of this particular lecture is to discuss about the cache operations. And our cache operations, the first operation is cache read. Okay. Second operation that we will be discussing will be cache write or data write. The third operation will be insert, inserting data into the cache. Fourth operation will be evict. And in the insertion also, we will discuss the replace operation. Fine. Now, let's first discuss the first operation, that is cache read. So whenever a processor has to read some block from the main memory or block from the memory, what it does, processor sends a read request. Okay, and this read request contains the address of that particular data. This read request goes to first to the cache. Okay. So basically with the cache, we have a cache controller. This cache controller receives the read request and it checks this address, and based on this address, it goes to one particular location, or we can say it will search in this particular cache depending upon the type of cache, whether it is a direct mapped cache, set associative cache, or fully associative cache. Depending upon that, it will check this particular address in this particular cache. So there are two choices. The first choice is data is found in the cache. And second choice is data is not in the cache. So if data is found in the cache, it is called cache hit. If there is no data in the cache, it will be cache miss. So if there is a cache hit, then in this particular scenario here, in this particular scenario, data is sent to the processor. Okay, and if the data is not in the cache, then a request is forwarded to lower level. Lower level means, let's suppose I have an L1 cache, and if there is a miss in L1 cache, we will forward the request to the L2 cache, and the last level will be the main memory. Now you can see that in this cache read, in this particular operation, let's suppose I am able to find the data into the cache. Then what I am going to do, I will take that data and will give that data to the processor. Okay. Now see, we have a cache, and cache, we have two arrays. One is the data array and The second one is the tag array. So tag array stores the tag and data array stores the data. Initially, at the beginning, initial point. At initial point, what will be there in this cache? So this cache will be empty. Okay. So that means all locations are available. Okay. Or I can say all locations contain dummy data. Dummy data means that it is of no use. Okay. Now let's suppose my request comes here to the cache, and this request will find dummy data in this particular entry or any entry. It will find the dummy data. But how will my cache controller knows, how will it differentiate between the dummy data and real data? So what is the difference? Or I can say, let's suppose this entry contains data and this entry is empty. Empty means it contains some dummy data. How will my processor know that this is the actual data, real data, valid data, and this is the dummy data? Or we can say, how will it know this location is filled and this location is empty? So how will it know? So there is no way it can know by this information. It can know if with every tag entry, it has an extra bit. Okay. And this bit will be, if it is 1, the value of this bit is 1. 1 means the data is valid. If this value is 0, it means the data is invalid. Invalid, we can say the data is dummy data. So this is dummy here. So if any entry has this value as 0, it means that particular entry is empty. However, if this value is 1, it means the space entry is occupied. So this particular bit that stores the information whether the data contained in this particular entry is a valid data or an invalid data, this particular bit is called a valid bit. Okay, so you should understand the importance of valid bit. So with every tag entry, we have one extra bit, and that bit is called a valid bit. And this bit determines whether the data is valid or invalid, or we can say whether that particular entry in the cache is empty or occupied. Okay. So this is about the cache read operation, and also how we can differentiate between a filled entry and an empty entry. Okay. Now let's move to other operation. The second operation is cache write operation. Like cache read, whenever a processor has to do a cache write, what it is going to do, it will send a write request plus address of that location. So this request will go to cache controller. This controller will have two options. One, entry is present in the cache. Second is entry is not in the cache. So the first one is cache hit and the second one is cache miss. Now in the cache hit scenario, in this particular scenario, it will simply write data at that location. And in this particular scenario, it will read data from lower level. Then first is read data from lower level. Second, put that data into cache. And third will be write new data at that location. So that means if it is not finding the data in the cache, that particular data which it wants to update. So if it is not there in the cache, it will get that data from the main memory. After getting that data from the lower level cache or from the main memory, it will first get into the cache and then it will update that data. Okay. Also, we know that cache entry, this entry contains a complete block. But there is a possibility that this write request is only for few bytes. So we don't have to modify the entire block. We should only modify these few bytes in this particular block, which are to be modified. Fine. Now the question arises, let's suppose I was having this cache. This was my cache. And let's suppose this was my memory, main memory. And let's say there is some block at this address, some block B1. Okay. And I have taken this block and put into the cache. This block B1 is here. Let's suppose it contains data 50. It also contains data 50. Now let's say my processor is saying that update this particular data, this particular block. So it will update it to 60. Let's say. Now, if we see here, we have the value of block B1 as 60, but here we have the value B1 as 50. This should also be 60 now. Why it should also be 60? Because my processor has updated this data. So in case of cache write, we have to not only write, or we can say update data in cache, but also in lower levels. Let's suppose we didn't update it in the lower level. There will be an inconsistency. At one place we have 60 value, and at other place for the same location we have 50 value. Okay, so this is required to avoid inconsistency. Now, so what I'm saying that if we have a cache write, we have to write not only into the cache, but we have to propagate that write to all the lower levels. Or let me write it here, propagate write to all lower levels in order to maintain data consistency. Now there are two choices of doing this propagation. Okay, so what are the two choices? The first choice is, choice one is to have a cache sorry, write through cache. And the second possibility, or we can say second type, is a write back cache. So what kind of policy we should use, or we can say what kind of cache we should use, write through cache or write back cache. And you have to remember that this difference is only because of this write operation, since we have to propagate write to all lower levels. Okay, so let's first discuss the write through cache. So in the write through cache, what happens whenever we have write in L1 cache or in any cache, we immediately send the update to all the lower levels. So that means whenever I am doing write in any cache, at that particular moment, I send that write to all the lower levels as well. So what does that mean? So if you come here, so it means that, let's suppose I was writing 60 here. So after writing 60, immediately I will send this 60 here. So there will be no inconsistency. Okay, so write through cache means that in this particular cache, whenever we have a write operation, we immediately send that particular update to all the lower levels. Okay, and this scheme is quite simpler. Okay, however, it has the limitation, and the limitation is that, let's suppose this is my cache, and this was some entry, and this entry is mapped to main memory is this particular entry. Let's say initially this is 60 and this is also 60. Now let's say a write comes, write 1. So write 1 is saying make this 70. So if this is a write through cache, I should immediately send this data here and make it 70 as well. Now let's suppose at the same time another request comes, another write request is there, make this 80. So immediately I will send this here 80. Now let's suppose another request comes, make it 90. Immediately I should make this 90 as well. Okay, so whenever we have write, we are also sending the request to the lower levels. So that is the limitation. Limitation is that it increases traffic. Okay, now let me give an example here. So see how many write requests were there. W1 was it make it 70, W2 was make it 80, W3 was make it 90. Okay, and each time we did an update into the main memory as well, when our cache was write through cache. Now I can decrease this traffic. How I can decrease this traffic? Instead of sending this data every time, this particular data every time to the lower levels, let's not send these data immediately. Write updates, let's not send these immediately. Okay, so what I mean to say, let's send the update only when we are replacing this particular entry. Okay, so what I mean to say, that if I was having this cache, so this was the entry, So this same entry, initially it was 60. Now W1 came, it became 70. Now W2 came, it became 80. Now W3 came, it became 90. And my main memory is still 60. Okay. I am not sending the data immediately to the main memory. Why? Because I want to decrease the traffic. Then what will be the problem? The problem is if I evict this. Evict means if I replaced this particular entry. Replaced this particular entry means that I got some block from main memory and I want to write that block here. Then in that case, if I simply evicted this particular entry from the main memory, from the cache, I will lose these updates, because I was that the final value in this block should be 90. So when I am evicting this, I am losing this information. In the first scenario, when I was having a write through cache, even when I was evicting, I was not losing any information. Why I was not losing any information? Because whatever updates were there, I was immediately sending those updates to the main memory. Now, if I am doing any eviction in the cache, my data is already updated in the main memory. But in the second scenario, where I am not immediately sending the write to the lower level caches, in that particular scenario, if I did an eviction, I will lose my updates. So at the time of eviction, I have to see something. What I have to see? I have to see if I have modified this block. If the block is modified, then update main memory and then evict. However, if the data is not modified means whatever the data was there in the cache, the same data is in the main memory as well. So if the data is not modified, simply evict. So in this particular scenario, am I increasing the traffic or decreasing the traffic as compared to write through cache? So here I have less traffic. Because why there is less traffic? Because I am not sending the modifications, or we can say I am not sending the update requests immediately to all the lower levels, but I am sending these write updates only at the time of eviction. Okay, so in the write through cache, evictions are simple. Evictions are simple. Why evictions are simple? Because I don't care whether the data has been modified or not. Even if the data has been modified, at that particular time, I would have sent that modification to the main memory. So if I do an eviction, I am not losing anything. But in the second scenario, what is the second scenario? So this was the first scenario. The second scenario, I am saying the write back cache. So in the write back cache, whenever we have write in cache, we don't immediately send the update to lower levels. Okay, then what we do when, so what we are going to do with every entry, we add an extra bit and this extra bit gives us information whether that entry was modified or not. Okay. So if the entry was not modified, so let me write it here. So there are two now choices. The choice one is the entry was modified. So if the entry was modified and then we have to replace that entry, or we can say we have to evict that entry, replace or evict. Then in that particular scenario, we will send that updated entry to lower levels so that we won't lose any update. However, if the data is not modified, if the entry is not modified, okay, so we can simply evict that entry. So you can see, for example, the difference between write through cache and write back cache is that write through cache, whenever we have an update, we will immediately update the lower levels as well. However, in the write back cache, the updates are sent to the lower levels only at the time of eviction. So in write back cache, only at the time of eviction, we decide whether an update is to be sent to the lower level or not. Okay, so in the write back cache, evictions are expensive. Evictions are expensive because at the time of eviction, we have to check whether the data has been modified or not. And how we decide whether the data has been modified or not, what we do when we have this tag entry for a cache, this tag, and this was data array. Whenever we modify some entry, let's suppose we have updated this entry. Okay, so for the tag, we add an extra bit that is called a modified bit. Okay, or this is also called a dirty bit. So if the value of this bit is 1, 1 means the data has been modified. And if the value is 0, it means not modified. It is clean. Okay, so at the time of eviction, we see this particular bit. If this bit is 1, 1 means that we have modified this data. So this modification is to be sent to lower levels. However, if the value of this bit is 0, 0 means that this particular data has not been modified. So we can easily evict this particular entry. Okay. So these were the two types of caches, depending upon the type of write operation. So we have a write through cache and a write back cache, and both these have their limitations and advantages. Okay, so this was the second operation. Now we have the third operation. The third operation is insert. So that means we have to insert data into the cache, or we can say insert new block into the cache. Into the okay. Now see, it depends upon what type of cache we are using. So there are three caches. One is direct cache, direct mapped cache. Second is fully associative cache. and third is set associative cache. So let's explain this operation for set associative caches. So if you understand it for the set associative cache, you will understand for fully associative as well as for direct. Okay. So let's suppose I have a set associative cache. So this is my set associative cache. So let's say every set. So let's take an example that there are 4 sets and every set contains 4 blocks. So block 1, block 2, block 3, and block 4. Likewise here. This is set 1, 0, set 1, set 2, and set 3. These are the 4 sets. Now let's say this is our cache and this is our memory, main memory. So let's say I am getting some block from here, block 1, and I have to insert this block into the cache. Now let's say this block maps to set S1. Okay. So what we will do, if it maps to set S1, now S1 contains how many blocks? S1 has 4 blocks. Okay. So block 1 of S, block 2 of S, block 3 of S, and block 4 of S. And we said this B1 maps to this particular set. So we can place this B1 in this block or in this block or in this block or in this block. So in which block we will place this particular block? Okay. So what we are going to do, we will see which one of these 4 blocks is empty. Okay. So how will we see whether which one of these 4 blocks is empty? We will check their which bit? Valid bit. So we will check the valid bit of B1 of S. We will check the valid bit of second block. We will check the valid bit of third block. And we will also check the valid bit of fourth block. Let's suppose this one is empty. B3 is empty. Then we will place this B1 at this particular block. However, so this is one scenario. The second scenario is, let's say all these 4 blocks are occupied. That means they are filled with some data. Then what we have to do? Then we have to choose one of these 4 blocks. Okay. Block 1, block 2, block 3, or block 4. We have to choose one of these 4 and we have to replace that particular block with this new block. Okay. So that means the scenario is, if all entries are full, then we need to choose one block and replace that block with a new block. Okay. But the issue is that since all these 4 blocks are occupied and we have to choose one, which one will I choose? Okay. Should I choose the first one, second one, third one, or fourth one? Okay. So depending upon the type of technique that we use to choose one among these 4, we have different replacement policies. Okay. So we have different replacement policies. So let's see some of the cache replacement policies. Okay. Let's see few. The first is random. Random means, so this random is saying that take any one of these four randomly, okay, and replace that particular block. So what it is saying, take any block randomly and replace with new data. So this is random replacement policy. However, this random replacement policy has performance issues. Why it has performance issues? Because it is not taking in consideration the program behavior. Let's suppose it is randomly choosing that particular block which is needed by the processor again and again. Then since we are replacing that block, so that means again and again we have to get that block from the main memory. Okay, so this policy is not a good policy. The second policy that is mostly used, not mostly used, or we can say the commonly replacement policy that is there, is first in first out replacement policy. What it is saying, this replacement policy saying that since we were having 4 blocks and all 4 were occupied, so let's say we first occupied this, so this was first occupied, this was second occupied, this was third occupied, and this was fourth occupied. Now since we have to place a new block, so which one should we replace? We should replace the first one which was occupied. So which one is the first one? The first one is this particular block. So we will replace this and put a new data at its position. So this is first in first out replacement policy. However, this policy also have a disadvantage. So what is the disadvantage? The disadvantage is, let's suppose the first one that came was this, then it was this, then this one, and then this one. Let's say my processor is repeatedly using this particular block, this B2 block, okay, repeatedly using. So since my processor is repeatedly using, I should have a policy such that this particular block will most of the time remain in the cache. But if I am using first in first out replacement policy, whenever I have a new block, I will replace this particular block. I won't care whether my processor is using it repeatedly or not. I am just checking the time when it first arrived. Since it arrived at the beginning, so I will replace this. Okay, so this particular replacement policy also have the disadvantage, or we can say limitation, is that in many scenarios it will replace that particular block which is getting used repeatedly. Okay, so the other replacement policy, and we can say the most commonly used replacement policy and the policy that have the maximum these performance benefits, is the least recently used replacement policy. But before discussing this replacement policy, you should understand how can we save the time here. Time in a sense, how will we determine which was the first block that arrived? So we can determine it by having a counter here. Counter here means that let's suppose this was the block that came, we will make its counter 0. Okay, now let's suppose this one came, we will make it 0 and update others, make it 1. Now let's say this one came, it is 0, this will be 1, this will become 2. Now let's suppose this one came, it will become 0, this will become 1, this will become 2, this will become 3. Now if I have to do the replacement, I can easily check from these values which one is the first in block. So based on the largest value of these, that one was the block that came at the beginning, and here this one is that particular block, the block with value 3. So using counters, we can determine the ordering of blocks. Ordering means in terms of time. Okay. Now let's see the least recently used policy. As I said, that this is most efficient policy. What is this doing? Let's suppose I have these blocks. These all were filled blocks, and now I have to replace one of these blocks. Least recently used is saying that I will see which one of these four was the least recently used. For example, let's take in real life. Let's say, for example, I had 4 books: book 1, book 2, book 3, and book 4. Okay, let's say today I am reading book 1. Yesterday I read book 2. Day before yesterday I read book 3. And day before that particular day I read book 4. So which one was the least recently used book? That was B4. And which one is the most recently used book? That is B1. So if I have to replace one of the books from these 4 books, I will replace that one which was least recently used, and that particular book was book 4. Okay, so likewise we have in these particular blocks, we will see which one of these blocks was the least recently used. For example, my cache is using these, my processor is using these blocks. Let's suppose it has used this 5 cycles before. It has used this 2 cycles before. It has used this 8 cycles before. And it has used this 6 cycles before. Now, if I have to replace one of these, I will replace this. Why? Because it was least recently used. Okay. Fine. Now, the question is, how will we determine which one was the least recently used? What we can do, whenever somebody has been used, let's suppose my processor is using this currently, I will add a timestamp in its tag entry, current timestamp. Okay. Likewise, everyone will have a timestamp. And whenever I have to replace anyone, I will check their timestamps. Whoever has the earliest timestamp, that one will be replaced. But it has the disadvantage that using a timestamp, it will make this process complex, because for every access we have to generate a timestamp and then add that timestamp into the tag entry. So instead of using a timestamp, we can use counters like we are using here. In first in, first out replacement policy, we can use the counters. So I'm not going to explain how we can update the counters, how we can use the counters. It is left as an exercise for you. Okay. So these were the 3 replacement policies that you can use in the cache. You can use a random policy, you can use first in, first out, or you can use least recently used. But this is the most efficient and most commonly used replacement policy. And what is this? Least recently used. Okay. So this completes our discussion about the insert operation. Now we have the last operation, and the last operation is evict, or the 4th operation related to the caches is evict operation. Evict means that I have to evict some of the block from the cache. Okay. Evict, when will I have to evict an entry? Whenever I have to replace that entry. Okay. Now in the evict operation, there are 2 scenarios. If I have a write through cache, what I will do, I will simply rewrite new block at its position. So it will simply replace that particular block, because in write through cache, we don't need to propagate anything. Why? Because every time we had an update, we propagated at that particular time. But the issue is with the write back cache. So in the write back cache, if we have to evict any cache line, or we can say any cache block, you can say cache block or cache line. It is one and the same thing. What we do, we first check its modified bit. So if modified bit is 1, or let us take first modified bit is 0, do nothing, just replace. However, if modified bit is 1, then first send an update to lower levels and then replace the entry, or we can say evict the entry. So this is about the evict operation. Okay. So with this, we completed the discussion about the different operations that we have to perform in case of a cache. Okay. So whenever you have a cache, whenever you have any cache, you should know following about the cache. First, you should know size of the cache. Second, you should know block size. You should know the mapping. And if it is set associative, you should know the number of blocks in each set. Fourth, you should know whether the cache is a write back cache or a write through cache. And the fifth important is you should know what type of replacement policy that cache is using. Okay. So these are the basic details that you should know about the cache. Okay. There are some other details also, but these are the basic details, and these are the details that are necessary for understanding this particular course. Other details are out of scope of this particular lecture, that those are usually discussed in high performance architecture courses. Okay. So with this, we have completed the discussion about the cache operations. Now we will discuss the entire memory system, or we can say how memory system is used in our pipeline. Okay, we will also derive some of the equations to calculate the cycles per instruction, or we can say CPI of a processor or IPC of a processor based on these cache designs. Okay, let's first discuss that particular memory model, then we will discuss the different types of cache misses. So let's discuss the mathematical model for the memory system. So now let's see how we can have a mathematical model for the memory system. Mathematical model here means that how this memory system affects the overall CPI of the processor. Now, before discussing this mathematical model, whenever in our computer system, we are discussing about the memory. So this memory includes both the caches plus main memory. Let's suppose caches are of size 2 MB, let's say, and main memory is 4 GB. Then the total size of the memory system is taken as 4 GB because the size of caches is negligible. However, when we are considering the memory system, won't mean only main memory. It will include these caches as well. However, we are only speaking about the address of the main, we are only speaking about the size of the main memory, because the other sizes are negligible as compared to its size. Moreover, see, if we have a main memory of 4 GB, okay, so let's suppose our processor is generating 32-bit address. So this 32-bit address, we know that each address, each entry has an address. So total, each byte has an address. So total number of bytes is 2 raised power 32 bytes. So 2 raised power 32 bytes is 4 GB. So using these 32-bit addresses, I can address all the locations of main memory. So these 32-bit addresses can address all locations of main memory. So all these locations of main memory make the address space of main memory. Or this is also called a physical address space. Not of main memory, but it is generally said as physical address space. So physical address space means all the locations that are there in the main memory. And this address that is used to map these locations of main memory, this address is called a physical address. So in simple words, we will say physical address is the address of a location in main memory, and physical address space is the set of all the locations that are there in the main memory. Okay. Now, in our pipeline, since we have to discuss about a mathematical model, in our pipeline, our fourth stage was memory access stage. Fourth stage was memory access. Okay, and we were saying that this memory access takes one cycle, but it is not always the case. So memory access means that we have to access the memory, and whenever we have to access the memory, we will first access cache. Okay. However, if there is a miss, then access other levels. Okay. So this memory access, when we were saying it will take only one cycle, so in that case, we were saying CPI is equal to 1. CPI 1, every cycle is taking one cycle. Okay, so in general terms, we can say CPI is equal to 1 when all the stages take one cycle. And this one is also called a CPI idle. CPI idle means that there is no penalty, there is no bubble, everything is uniform. Okay, there is no penalty in this particular pipeline. In that case, CPI idle is equal to 1, or we can say CPI is equal to 1. But we know that this is not always the case. This is case in memory access. We will say it will take one cycle only when there is a hit in L1 cache. However, if there is a miss in L1 cache, then it won't take one cycle. It will take more than one cycles. Okay, so we can say that in that particular scenario, our CPI will be equal to CPI idle plus extra cycles that are required in the memory access stage. We are not considering about the other stages. So other stages may have their own penalties, may have their own bubbles, but we are only considering here memory access stage. So it will be CPI idle plus stall rate into stall cycles. What I mean to say, let's suppose I am in some of the instructions, my memory access is getting hit. Okay, is getting hit means that it will take only one cycle. However, in some of the scenarios, I am getting a miss. So if I am getting a miss, that means there will be penalty. Okay, so that particular penalty is added here. So this is the penalty of miss. Penalty of miss. Because in a miss case, I have to search in the lower levels, and that will take more cycles. Okay, so what will be this penalty of miss? So penalty of miss will be stall rate. Let's say f of memory, it represents the fraction of memory instructions. So total fraction of memory instruction. Fraction here means, let's suppose I have 10 instructions, and out of these 3 are memory instructions. So this FM in that particular case will be 3 divided by 10, that is 0.3. So let F mem is the fraction of memory instructions, and AMAT is the average memory access time. So average memory access time here means the average time taken by each instruction. So average time taken by each instruction. Now we are saying AMAT, average time taken by each instruction. Now in the idle case, AMAT is equal to 1. Okay, AMAT is equal to 1 means hit is there. So in that particular case, CPI is equal to CPI idle. However, we don't have an ideal case. We have a real case. Real case means that there will be this penalty. And this penalty will be for this stall rate. Stall rate means how many memory instructions are there, fraction of memory instructions, and how many cycles, extra cycles we have to do for every memory instruction. So CPI will be equal to CPI idle plus fraction of memory instructions. So how many are the total instructions and what are the extra cycles? So extra cycles, so actual cycles should be 1, but total cycles are AMAT, average memory access time. So the extra cycles will be AMAT minus 1. So these are extra. So it will be AMAT minus. Okay, so this is the actual equation. But you have to remember that here we have only included the penalty incurred in memory access stage. In the actual equation, we have to include all the penalties because of other instructions or because of other dependencies. So this is our equation, memory equation. However, there is one important topic here, or we can say one important component, that is average memory access time. And we have already discussed this, average memory access time. So what is average memory access time? Average memory access time is, what is this? L1 hit rate into time taken to access L1 plus L1 miss rate into L1 miss penalty. And this will be equal to this part. So let's say it is A plus L1 miss rate, L1 miss rate into L1 miss penalty. L1 miss penalty means that what we have to do whenever there is a miss in L1. So we have to go to L2. So that means time taken to access L2, plus L2 miss rate if there is miss in the L2 into L2 miss penalty. Okay. Likewise, I can extend it to multiple levels. Let's suppose we have n levels of cache of memory, then we can extend this average memory access time. So I'm not going to discuss it in detail because we have already discussed about this in our last lecture. However, with this equation, you have one thing that will decrease your average memory access time. So what will decrease your average memory access time? So either increase hit rate, so it will increase hit rate. So we have to decrease average memory access time. So how we can decrease it? Increase hit rate, L1 hit rate, or we can say, or this can be said as decrease L1 miss rate and decrease miss penalty. So these are the two things. So to decrease average memory access time, we have to do two sophistications or two additions. First is decrease misses in the cache. Second modification or improvement that we can do is decrease miss penalty. These are the two things that we can do to decrease the average memory access time. So let's first see how we can decrease misses in the cache. But to discuss how to decrease misses in the cache, we should know what are the different types of misses. Okay. So after discussing these different types of misses, then we will see how we can decrease each type of miss. So that is the first part. Second part, we have to discuss how we can decrease miss penalty. Let's first discuss what are the different types of misses in the cache and how we can decrease each type of miss. Then we will discuss how we can decrease miss penalty. Okay, so let's first discuss what are the different types of misses in the cache. Okay, so there are three types of misses in our caches. So as I said that there are three types, and those three types are also called 3 C's. Why 3 C's? Because these are three types of misses. One is the compulsory miss. The second type of miss is the capacity miss. And the third type of miss is the conflict miss. So these are the three types of misses that are there in the caches. And these are also called the 3 C's. Let's discuss each of this separately and let's see how we can decrease each miss rate. Okay, because our aim is to decrease the number of misses. So first is the compulsory miss. So these are also called cold misses. So what are these misses and why the name compulsory? Compulsory means that these misses are going to happen. So what are those misses? For example, when my program is starting and at the beginning, there is nothing in the cache. So whenever in the beginning or whenever the first time it needs a data, there will be a miss because that data won't be there in the cache. We will bring the data in the cache only when it is needed. And at the beginning, there is nothing in the cache. So we can say that compulsory misses are misses at the beginning. Or we can also say when we require a block at first time. At that first time, the miss will be there. This compulsory miss will be there. So whenever we need a block for the first time during our complete execution, then at that first time, there will be a miss. Okay. And how we can decrease these types of misses? There are two solutions. Solution one is increase block size. So let's suppose I require 3 bytes, or let's suppose I require 100 bytes. Okay. And those bytes are one after the other. So if my block size is largest, so all those 100 bytes will be in a single block. So that means if I am accessing the first byte, so I will bring that block into the memory. And if I need the second block, third block, fourth block, because of the first block, they will already be there in the cache. So I don't be having the compulsory misses for the next bytes. However, let's say there are only 10 bytes in a block, and I said that I have to access 100 bytes. So for the first byte, I will be having a compulsory miss. So I will get a block containing the first byte, and that block contains 10 bytes. So now for every 10, I have one compulsory miss. Okay, so how many I have to do? I have to do 100 bytes. So for every 100, there will be 10 compulsory misses. Okay. However, if I have a block size of 100, then for that 100, I will have only one compulsory miss. So increasing the block size decreases the compulsory misses. However, increasing the block size has its disadvantages. So what are the disadvantages? The disadvantage is that there is a possibility that I am getting the unwanted data. So let's suppose the block size is 100 and I need only 1 or 2 bytes. Then for needing those 2 bytes, I am getting the 100 bytes. And that will result in cache pollution. So some of the data is without any use, it is occupying the space in the cache. Okay, so increasing block size can decrease the compulsory miss, but it has its disadvantage. The second solution is prefetching. What does that mean? Prefetching means that to have a mechanism that we can prefetch the data, we can get the data into the cache even before our processor needs that data. And how will we do that prefetch? So for example, if I need byte 1, how will my computer system know that I will require byte 1 without I sending any address? Okay. Because what I am saying here, prefetching means prefetch the data before it is used. So we need some prefetching techniques, those techniques that will help us what type of data, what is the probability that some data will be accessed. So I will keep that data into the cache before it is getting accessed. So let me give an example. For example, let's say my program is accessing an array. So let's say it is accessing the first byte, then second entry, third entry, fourth entry, fifth entry. During its access, let's suppose my process is getting first entry. First entry means first data, then second entry, second data, then third entry, third data. I can use a prefetch technique. I can use a hardware prefetcher. So this hardware prefetcher, it will see the nature of my processing, or it will see how I am getting these data elements. It will see that after getting the first, I am getting second. After getting the second, I am getting third. So what it will do, it will say that Since it is processing third, so there is a probability that it will need 4. So when it is processing the third item, we will prefetch the 4th item, 5th item, and 6th item. Okay, so there will be compulsory misses for only these 3. For these 3, because of prefetching, there won't be any compulsory miss. Okay, so there are multiple prefetching techniques. There are n number of techniques that are used to prefetch the data. Okay, however, that is out of scope of this particular lecture to discuss all those techniques, but you can look at the material that is available on the internet and look at different prefetching techniques that are already there in the literature. However, the prefetcher that I am using, the prefetcher that I want to use to prefetch the data from the memory, it should have good accuracy. If it is having poor accuracy, that means it is getting the unwanted data into the cache. And getting the unwanted data into the cache will replace the useful data into the cache, and that will result in cache pollution. So having a poor prefetcher will result in cache pollution. So you should choose the prefetcher so that you have a good prefetching accuracy. Okay, so this was about a compulsory miss and what are the 2 techniques that can be used to reduce the compulsory miss. Now let's come to the capacity misses. So capacity miss, as the name suggested, it is because of the less space availability. What does that mean? Let's suppose I have a cache and it can occupy only 10 blocks. Now, if I want to fetch 11th block, then because of the capacity of the of this cache, limited capacity of this particular cache, I won't be able to fit the 11th block. So I have there will be a miss and I will have to replace that block into the cache. And you have to remember, so the capacity miss will be there when the working set of a program is greater than size of the cache. What does that mean? What is the working set? Working set of a program. Working set means the number of blocks or the set of blocks that a program is accessing in a given amount of time, given interval of time. So if it is accessing large number of blocks and our cache does not have a capacity to hold those number of blocks, there will be large number of capacity misses. Okay, and this type of miss can only be decreased, these types of misses, by increasing the capacity. Capacity of cache. Okay. So this was about the capacity miss. Now comes the conflict miss. What is the conflict miss? So this type of miss is there in the direct mapper cache and set associative cache. These conflict misses. What is the meaning? For example, in direct mapper cache, I have a block here, block B1. Let's suppose I am getting another block from main memory, and this also maps to this location. Even if there are 3 locations here, since it is mapping to this location, so I cannot place this at other locations. So there is a conflict between this block and this block. Okay, so my processor needs block B2, but in the cache at that location there is block B1. Okay, so because of conflict between B1 and B2, I was not able to keep the B2 in this location. And when my processor needs B2, I will receive a miss. And by having that miss, I will replace B1 and keep B2 here. Okay, so because there was a conflict between B1 and B2, there was a miss. Okay, this type of miss is a conflict miss. Likewise, such kind of miss will occur in a set associative cache as well. Okay, so what I am saying that, see, this was a direct mapped cache. At this location, at this particular point, we know, let's suppose it maps B1 and B2 block. Now, since there is only one location, I can place only B1, let's say. Now, if my processor needs B2, it will check that B2 can be present here. But since this place is already occupied by B1, so there will be a miss. Okay. And so this miss is because of conflict between B1 and B2, because they were mapping to the same location. Okay. That is a conflict miss. And this conflict miss can be reduced by increasing associativity. However, if we increase the associativity beyond a certain limit, that has its disadvantages. That will result in more energy consumption, energy and power consumption. Okay. So these were three different types of misses, and I have also given a broad overview, or we can say a small overview of different solutions to decrease these misses. However, there are two thumb rules that you can keep in mind for decreasing the number of misses. Okay, so what is the thumb rule? The first thumb rule is that miss rate is inversely proportional to the square root of cache size. So if cache size is more, miss rate will be less. If cache size is less, miss rate will be more. So this is also called a square root rule. So there is no mathematical proof for this rule, but this holds in most of the scenarios. The second thumb rule is also called a associativity rule. And what is this associativity rule? It is basically saying that doubling the associativity has the same effect as doubling the cache size. What does that mean? It means that, let's suppose I have 128 KB two-way set associative cache, and I have another 4 KB four-way set associative cache. So you can see there, here we have doubled the associativity. Here it was 2, here it is 4. So doubling the associativity has same effect as doubling the cache size. So cache size was 64 KB. So this particular cache will have same effect at this particular cache. It will be equivalent. Okay, so this is the associativity rule. And again, this rule does not have any mathematical proof. It is an empirical formula. Okay. So this was all about the misses that are there in the cache systems and how we can reduce these misses. So we completed the different types of misses and different mechanisms to reduce the miss rate. Now our discussion, or we can say the last discussion of this particular lecture, is to decrease the miss penalty. What are the different techniques that we can use to decrease the miss penalty? Okay, so we will only discuss 1 or 2 techniques, but there are many other techniques to reduce the miss penalty, but those are out of scope of this particular lecture. So now let's discuss how we can decrease the miss penalty. So we have to see techniques to reduce miss penalty. I will only briefly discuss 1 or 2 techniques. So the first one is use a write buffer. Okay. So let's see how this decreases the miss penalty. See what this write buffer is used and how it decreases the miss penalty. So let's suppose we have to do a write. So processor sends a write request. Okay. So when it is sending a write request to a cache, okay, a write request. So let's say there is a miss. So when there is a miss, how will our system respond? It will go to the main memory or to the lower levels. It will get that block, place that block here, then update that block. After updating the block, it will send that block to the lower levels. Okay. So you can see that first we have to get a block, then we have to update that block, then we have to send that block to the main memory or to the lower levels. Then only we can move to the next operation. So here miss penalty includes, because there was a miss. So miss penalty includes, one is getting data from lower level plus updating data plus sending updated data to lower levels. Okay, this is the miss penalty in this particular scenario. However, we can simply omit out this part, this particular part, by using the write buffers. So how? What we are going to do with every cache, so if this is a cache, we will have a small buffer called a write buffer. And this is our main memory. So how it works? So let's suppose we have processor send a write request. So let's say there was a miss. So because of miss, it will go to main memory. It will get the block. Okay. And it will update the block. After updating the block, it will send the block to write buffer. Okay. And sending the block to write buffer, it won't care what is happening after that. Okay. It will now work on its own. So this write buffer then sends the data to the other levels, to other caches, and to the main memory. Okay. So now our miss penalty will be get data from lower level plus update data plus send to write buffer. Okay. Here it was send update data to lower levels. The lower levels can be L2 cache, then L3 cache, then L3 main memory. So L2 plus L3 plus main memory. However, here it is only send to write buffer. Then start your own job. Okay. So this miss penalty is lesser than this particular miss penalty. And it was possible only using the write buffer. So the write buffers can decrease the miss penalty, but they don't have a large effect on the overall performance. But yes, there is some significant effect on the overall performance, or we can say in decreasing the overall miss penalty. So this is one technique where we can decrease the miss penalty in case of a write request. Okay. The second technique is called critical word first, or it is also called early restart. So The previous one, the first solution was for write, when we have a write miss, and this is for when we have a read miss. Okay, so let's see the scenario. The scenario is, this is cache, this is main memory. Let's suppose processor sends a request for byte, some byte 3, or let's suppose 3 and 4, byte 3 and 4. Let's say these bytes are there in block 1. Okay, and block 1 is not in the cache. Okay, so there is read miss. What I mean to say read miss, that my processor wanted this particular block, and in this block it wanted these 2 bytes, but this block is not in the cache, so there is a read miss. What will happen? It will go to the main memory, it will get this block, place this block here, this block B1, place this block here, and then use these 2 bytes. So let's say block 1 is 32 bytes. So it has to get 32 bytes, then it can use these 2 bytes. Okay. So this is a general approach. Now, if we change this approach, so what I mean to say, how we can change this approach, my processor needs these 2 bytes, and there was a read miss. So while I am getting the bytes from main memory, basically I am getting a block, and block contains bytes. So while I am getting bytes from the main memory, whenever I get these bytes, I won't wait for other bytes to come. I will directly send these bytes to processor, and that processor will use these bytes instead of waiting completely for these blocks, for this complete block. Okay, so whenever I am getting these words or these bytes that are needed, so instead of waiting for the entire block, I will send these bytes to the processor, and my processor will work on these bytes. It doesn't care about the other bytes. Okay, so in parallel, I am getting the other bytes, and at the same time, I am using these bytes that are needed. So these bytes that are needed, these are also called critical words. So I am getting the critical word first from the main memory, and I am sending that word to the processor, and my processor will use that particular word instead of waiting for other words. So it is called, as a result, this particular scenario or this particular technique is also called a critical word first. Get the bytes that are needed first, get the critical words that are needed first from the main memory, and instead of waiting for other bytes, allow processor to work on those bytes. So as a result, it is also called early restart. Early restart means even before waiting for all the bytes, it will start its job, and this will decrease the read miss penalty. Okay. So these were the 2 techniques. The first technique was to reduce write miss penalty, and the second technique was to reduce read miss penalty. With this, we have completed the discussion about decreasing the miss penalties. And with this, we have also completed this particular lecture. So in this particular lecture, we first discussed what are the different cache operations that are possible. Then we discussed the mathematical model related to the memory access. Then we discussed the cache misses and how we can reduce the miss rate in different types of caches. Then at the end, we discussed how we can decrease the miss penalty by using these 2 techniques. Okay, so with this, I will stop this particular lecture, and we will discuss about the virtual memory in our next lecture. So let's meet in the next lecture. Till then, goodbye.